Recording.
Okay, so next time we're going to get Kaifi to add some practical onto this so that we can have a real example. But the Doppler effect, it's that sound as like a motorbike goes zooming past you. Or any kind of body that's emitting a sound goes past you. That sound is higher when that body is coming towards you, and then lower when it's moving away from you. Or at least that's how we experience that sound. The frequency of sound emitted by the whatever object's moving. Like if you're inside the motorbike, you don't hear the sound of the motor change when you're going towards someone compared to when you're going away. Like the sound of the motor stays the same all the time, but we experience it differently. So it's not really a change in frequency, it's just an apparent change in frequency. So, Doppler effect, it's the apparent change in frequency due to the relative motion between the source and the observer. And for us, this year, the observer is always going to be stationary, and it's only ever the source that's moving. And crazily, it makes a difference. Like, it's different if you go running towards someone sitting there on a motorbike revving the engine, and you run at the same speed the motorbike's driving. You get a different change in frequency than if the motorbike is driving towards you, which is just mind-boggling. But we are only going to look at the change in frequency due to a moving source and a stationary observer. And so say that's your moving source, like that. One really good way of understanding this is to draw on the sound waves. And so the sound waves are moving at a constant speed no matter what direction they are. And so if we're going to draw like the wave fronts of the sound waves as they emanate outwards from that source, they're going to be like, it's like dropping a pebble into a pond. There's going to be concentric circles. And so perhaps what we'll do is just, first of all, if we had our source stopped, if the V is 0, and it's just sitting there, just to make sure we've talked about like the nothing happens scenario, those wave fronts are just going to look like concentric circles moving outwards. So those are the sound waves moving outwards from the source. So when the source speed is 0, it's like dropping pebbles in the ocean or in a puddle, that those sound waves just move outwards from the source like that. However, if we take our source and we start to move it forwards, we're still going to get those concentric circles, but what's happening that causes this change in frequency is between emitting one wave and the next one, our source moves forwards. So it's like your pebble drops in one place, then the next pebble drops a little bit further forward, and the next one a little bit further forward, and so your little concentric circles aren't all coming from the same place, they're coming from different places. And so even if the innermost one looks like that, we'll look at the previous one and see that it's centered on where you used to be, and then the previous one is centered on where you used to be. And so what we end up with is that the sound waves in front of a moving source get compressed together, the wavelength gets decreased, the frequency gets increased because the wave speed is constant, whereas behind it the wavelength gets increased, which means the frequency is decreased because the wave speed is constant. Out to the sides, what happens?
Kind of compressed, kind of not compressed.
How much is the source moving upwards and downwards? So how much compression occurs upwards and downwards? None. So there's no change in frequency when you're perpendicular to the source, like it's moving past you, there's no compression that way, and so there's sort of like zero.
So if you were directly above them, what
That doesn't make sense though, because wouldn't that have the same logic for being horizontal to it? It's not moving
If you're
sideways.
standing- so as the motorbike goes past you, you hear, but then when it's right in front of you, so when it's right next to you, you hear the correct frequency. As it goes past you, you hear its real frequency.
Yeah. Okay.
And that's exactly the same if you're standing here in the horizontal plane with that. You're going to hear the correct frequency, true frequency of the source as it passes next to you, and as no component of its velocity is towards you or away from you, you're going to get no compression.
And say if you were right above it, stationary, but it was moving, it's just that.
So here we get max compression.
But surely, if you were moving fast enough, the top and bottom and sides would compress, right? Because it's like this. If like you emit one here and then move to there and then emit one, then like these two balls kind of like are stacking, right?
The key thing to think about is whether there is any velocity towards or away from the observer. Is the source velocity towards or away from? So like no matter how fast the source is moving, if it's not moving towards you or it's not moving away from you, if it's just going past you, you're not going to observe any change in frequency. Okay, stick with me, this bit's hard. In front of the source, how much is the wavelength going to have decreased by? We're trying to put numbers on this. It's going to have decreased by however much the source moves forward in the time it takes to emit one wave. The time it takes to emit one wave, we call that the period of the sound, eh? And so lambda, change in lambda is going to be the source speed times the period. And that change in wavelength is going to be the same in front and behind the source. Change in wavelength is just going to be the source speed times by the period. Ask again.
So, but how come the wavelength gets smaller, one gets bigger? Is that because it's like positive and negative?
Yeah. So in front of the source, the new wavelength, lambda prime, is going to be the old wavelength, take off the source speed times by the period. And thinking about the period of the wave, the period is the same as the, how can we rewrite period?
1 over f.
1 over f. So t is 1 over f. And also we know that lambda is v over f. And we're also we're going to keep track of the changed frequency and the original frequency. So lambda prime is going to be v over f prime. So instead of writing lambda prime, we're going to write v over v. We're going to keep track of our v's, right? We've got two v's. Now things are getting complicated. We've got our source speed and our wave speed. So Vw, speed of the wave, Vs, speed of the source. So Vw over f prime is equal to Vw over f minus Vs over f. And what we would like to do is rewrite this with a common denominator. So Vw over f prime is Vw minus Vs over f. like to get the f prime up the top. So we're just going to multiply the two f's across up to the top line. So we're going to have f prime vw minus vs equals f v w. Sorry, that's a double.
Is this just for in front of the source?
This is just for in front of the source. And now we're going to f prime equals f vw over vw minus vs. The key difference, if we look at what's happening behind the source, is that behind the source, the lambda prime is going to be the lambda plus the s t. Compare that to what we started with over here. We had a minus. So the only difference between what happens behind the source and what happens in front of the source is whether it's a plus or a minus. So we can rewrite this more generally, that will apply to everywhere, as f prime is f vw over vw plus or minus vx. The minus is what we're going to use when the source is approaching, and the plus is when it's receding, it's moving away from us. So that f prime is the new frequency, the changed frequency. The f is the original frequency. The vw is the speed of the wave, and the vs is the speed of the source. So it's really easy to get that vs confused with speed of sound. Vw is the speed of sound. Vs is the speed of the source.
Yeah, I hadn't even thought about that, but now you say that, probably will get confused.
Yeah, be careful. Be careful about which one the plus is for and which one's the minus for. Our way of remembering it with no logic but that works is that when the distance is decreasing, it's minus.
Yeah.
The distance is decreasing, the thing's getting closer to you, it's minus. The distance is increasing, it's plus. It's a way of remembering.
That's easy.
There's something.